Welcome back to the Deep Dive. Today we are dispensing with the pleasantries and the usual slow rollout.
Oh, jumping right in.
Right in. Because we're not just analyzing a trend report. We are stepping directly into a war room.
Hmm.
The date on the simulation is February 15th, 2026. If you are a lead engineer, a technical director, or maybe a CTO listening to this, you know the ground has already shifted beneath our feet.
It's a completely different landscape than it was even 2 years ago.
It is. We have the Global BMS Technical Strategy Report for 2024 to 2026 right here in front of us. And frankly, looking at this document, it reads less like a spec sheet and more like a survival guide.
It is absolutely a survival guide. And the reason we have to frame it that way is because the definition of the component itself, the battery management system, it's gone through a fundamental identity crisis over the last 24 months.
An identity crisis. How so?
Well, we used to look at the BMS as a gatekeeper.
A glorified switch.
That's it. A glorified swish. Its job was simple. Keep the voltage within a safe window, balance the cells a little bit during charging, and if things got too hot, open the contactor.
Job done.
Job done. It was a passive monitoring guard.
Right. So if the house caught fire, it called the fire department.
Yeah.
But looking at where we are now in early 2026, the mandate from the boardrooms, and let's be honest, for the regulators in Brussels, Washington, and Beijing, it has totally shifted.
Totally.
The new mandate is zero tolerance.
Yeah.
They don't want a fire containment strategy.
No. They want fire prevention before the first wisp of smoke even appears.
Exactly. And that shift from mitigation to prevention, that requires a massive leap in technical capability.
It's huge. We are moving from a reactive system to what we're calling a proactive brain.
A proactive brain. I like that.
We're being tasked with finding faults that haven't even happened yet. We're looking for the ghost in the machine.
Which brings us to our specific role today. We're acting as your senior technical strategy consultants. We're taking this massive, dense report, and we're going to distill it using a strict, top-down MECE approach.
Mutually exclusive, collectively exhaustive.
Exactly. We've identified 4 pillars
that
really define the engineering roadmap for this year. And I'll say this, if you miss one of these pillars, your platform is obsolete.
It's that critical, so let's lay them out.
Please.
Pillar 1 is algorithmic intelligence. This is the big shift from pure physics-based models to hybrid AI. It's all about how the BMS thinks.
Okay, the brain.
Then Pillar 2 is hardware architecture. Here we're talking about surviving the violent electrical environment of 800-volt silicon carbide systems.
And the wireless trend.
And the radical move to wireless BMS. That's the body.
Got it. Brain and body. What's 3?
Pillar 3 is the development paradigm. So how do we test this stuff without spending 5 years and $50 million crashing cars?
The virtual world.
Exactly. We're moving to virtualization and digital twins. And finally, Pillar 4. This is global compliance. It's the geopolitical and regulatory landscape, specifically the battery passport and the ongoing supply chain wars.
Okay. Before we dissect Pillar 1, I want to highlight something. A specific finding from the IAV source material that actually made me, pause.
Oh, I know the one you're talking about.
It's a hook that really sets the stage for why the old methods are dead.
Mm-hmm.
They explicitly stated that if you are relying on a temperature sensor, thermistor, to detect a thermal event, you have already failed.
That is the single most critical aha moment in all the recent data. It changes everything.
Why, though? Walk us through the physics.
Think about it. By the time a thermistor, which is glued to the outside of a can or a pouch cell.
Right, it's on the surface.
By the time it picks up a heat spike, the internal chemistry is already an exothermic runaway. You are past the point of no return.
So you're just watching the fire start at that point?
Yeah. You're managing a disaster, not preventing one. The game is now entirely about detecting the internal short circuit, or ISC, days or even weeks before heat is ever generated.
Days or weeks.
And here is the kicker, which we're going to unpack. The most dangerous time for a battery and the best time to catch a fault, it isn't when you're driving 100 miles an hour.
It's when the car is parked.
The idle phase.
The idle phase. It's so counterintuitive. We spend millions optimizing the drive cycle, but the real safety war is won in the parking lot.
It is.
Okay, let's get into the weeds. Pillar 1, the algorithmic pivot from physics to hybrid AI.
Right. So to really understand the solution, we have to understand the adversary. And the adversary here is the soft short.
A soft short. Define that for us.
We are talking about a micro short. Maybe it's caused by a lithium dendrite that's slowly piercing the separator, or a tiny particle of copper contamination from the gigafactory.
Something you'd never see with the naked eye.
Never. We are talking about resistance values between, say, 100 ohms and 10K ohms.
Okay, and just to put that in context for the electrical engineers listening, a 100 short in a 4-volt cell is pulling, what, 40 milliamps?
Exactly, 40 milliamps. That generates negligible heat. It's milliwatts of power.
Hmm,
A thermistor will never, ever see it. It's invisible to thermal imaging.
but it's not harmless.
Oh, no. That 40 milliamps is slowly, silently draining the cell. It creates this tiny voltage imbalance over time, and eventually that dendrite grows. It gets thicker.
So the resistance drops.
The resistance drops, the current spikes, then you get the hard short, the arc, and the fire. Our job is to catch it at that 40 milliamp stage.
Which brings us to the first level of defense in the report. Level 1. Recursive least squares, or RLS. This is the bread and butter of the legacy auto industry, right?
It is. Most cars on the road today are running some version of this.
So walk us through why this is the baseline, and more importantly, why it's now failing.
Sure. RLS is essentially a linear mean difference model. Inside the BMS chip, you have what's called an equivalent circuit model, an ECM.
In ECM,
Like,
right?
Usually it's a Thevenin model, so you have an ideal voltage source, that's your OCV, a series resistor, R0, which represents the immediate internal resistance,
And then some capacitors and resistors to model the other effects.
and maybe one or two capacitor-resistor pairs, your RC pairs, to simulate the polarization and diffusion effects.
Yes. So it's a mathematical drawing of the battery.
Wow.
And the RLS algorithm is constantly comparing the real voltage it's measuring from the ADC
Analog to digital converter, yep.
against what the math model predicts the voltage should be.
Right. It calculates the residual, the error. If that error is high, it updates the parameters in the model. It says, oh, the internal resistance must be higher than I thought, and it adjusts the model on the fly.
It's a self-correcting filter.
It is. And it's very good at estimating state of charge, SOC, and state of health, SOH, when the changes are global, like when the whole battery is aging uniformly.
But here's my issue with it. For safety, it assumes the error is due to a parameter change in a healthy way. But if I have a microshort, that looks like a parallel resistance, not a series resistance change. Does RLS even distinguish between a degrading cell and a shorted cell?
And that is the fatal flaw. You've hit it exactly. RLS suffers from what we call covariance windup. It just lacks the excitation it needs,
Flaming.
meaning it struggles immensely to separate a soft short from simple sensor noise or just normal aging. If the short is 10K ohms, the current leakage is so small it gets completely lost in the noise floor of the current sensor.
So it's blind to the real problem.
RLS is a blunt instrument. It's great for catching a cell when it's already dead, not when it's just getting sick. It looks for gross errors, not these subtle, dangerous cues.
Okay, so RLS is out for early detection. It's still useful for SOC, but not for safety. That brings us to level 2, Shannon entropy. Now, this sounds like we're moving from electrical engineering into information theory.
We are, and this is where that parking insight becomes so critical.
Right, the idle phase.
Shannon entropy measures the disorder or the uncertainty in a dataset. The formula is Hx equals the negative sum of Px log Px.
Okay, in plain English.
In plain English, a healthy battery at rest is ordered. The voltage settles down and stays flat. It has very low entropy.
Okay, simple enough. And a sick battery.
A sick battery with a microshort is disordered. Even when you park the car and walk away, that tiny leakage current, that 40 milliamps we talked about, is causing the voltage to fluctuate ever so slightly.
It's restless.
It's chemically restless, the entropy score rises, it becomes a noisy signal.
I read in the report that the golden window for this is specifically that parking phase. Why then? Why not while driving?
It's all about the relaxation curve. When you turn off the car, the battery voltage doesn't just drop to its resting state, it relaxes back to its open circuit voltage. This process takes hours. A healthy cell relaxes smoothly, following a predictable logarithmic decay. A shorted cell, though, it has a secondary reaction fighting against that relaxation. So if you bin the voltage data over a, say, 6-hour parking window, and you calculate the entropy,
A shorted cell sticks out.
it screams at you. The report calls it a permanent entropy rise.
That is brilliant because it turns the noise, which RLS ignores, into the actual signal.
Exactly.
You don't need a super precise current sensor. You just need to analyze the distribution of the voltage jitter over time.
Yeah.
But let's talk implementation. Running an entropy calculation on a microcontroller, is that computationally heavy for the BMS chip?
It's manageable. It's not as light as RLS, but it's
Right.
not, well, it's not what's coming next. Shannon entropy is just statistics at the end of the day. You can run that on a standard automotive MCU, an Infineon RX or an NXP chip.
Okay.
But level 3 and 4, that's where we hit the hardware limit. That's where we leave the domain of statistics and we enter the domain of artificial intelligence.
Let's talk about that. Level 3 is random forest, and level 4 is autoencoders. Now, we are deep in the buzzword territory. But for a director of engineering listening to this, the question is simple. Do I put this on the chip, or do I put it in the cloud?
That is the core strategic debate right now. Level 3 random forest is a knowledge-based approach. What that means is you, the engineer, you manually extract features from the data.
So you're telling the algorithm what to look for.
Precisely. You tell it. Look at the time it took to charge from 20% to 80%, or look at the energy loss during the last drive compared to the previous 5 drives. You feed these hand-picked features into a decision tree, or rather, a forest of them.
So it's a very sophisticated if this, then that.
Yes, but thousands of them nested together. The IAB data shows it hits about 80% accuracy.
80% sounds pretty good.
It is, and the benefit is that it's interpretable. If it flags a fault, you can actually trace back down the tree and see why. It can tell you, I flagged this because the charging time was 12% shorter than the historical average.
But 80% accuracy also means 20% error. In a fleet of 1 million cars, that's 200,000 false alarms. That's a recall nightmare.
It's a PR disaster.
They just can't have it.
You absolutely cannot have false positives in a safety-critical system. You can't brick a customer's car on their way to the airport because the algorithm thought it saw a ghost.
Which is why the report positions autoencoders, level 4, as the holy grail.
This is the holy grail. This is deep learning. It's unsupervised, or more accurately, semi-supervised.
Explain the semi-supervised part, because normally, to train an AI to find fires, I'd need to show it thousands of examples of fires, and thankfully we just don't have that data.
Correct. We have a massive data imbalance problem. We have billions of hours of healthy driving data and almost 0 hours of fire precursor data. So we flip the script. We train the autoencoder only on the healthy data. We build a neural network that's forced to compress the input data into a tiny bottleneck, a latent space, and then reconstruct it back to the original format.
So it learns to paint a perfect picture of a healthy battery. It becomes a connoisseur of perfection.
Yes, it learns the essence of what a good battery looks and behaves like. Then, in the field, when a faulty signal comes in, even with a tiny, tiny deviation, the autoencoder tries to reconstruct it using its healthy rules, and it fails.
It can't paint the picture correctly.
It can't. It generates a high reconstruction error. That error value is your fault signal.
I love the stat here from the IAV study. It's just incredible. It detected a fault 8 days earlier than traditional methods.
8 days.
That's a lifetime. That's the difference between a garage fire and a simple service battery soon light on the dashboard.
And look at the deviation it caused.
The voltage deviation was only 6.8 millivolts.
6.8 millivolts. I mean, that is deep in the noise floor. Most BMS chips have a measurement error of plus or minus 2 milliV anyway.
Yeah.
So finding a 6.8 RV drift over a week is like, it's like finding a needle in a haystack while the haystack is on a moving train.
But here's the rub, and this is where my advice to the client comes in. You cannot run a deep autoencoder on a standard BMS chip. It's just too heavy.
Way too heavy.
It requires matrix multiplication capabilities that a standard safety MCU just doesn't have.
So the consultant's recommendation has to be a fusion strategy.
So we don't pick one algorithm, we use them all.
We layer them. Imagine this architecture. The car is parked. The low-power BMS chip wakes up every hour or so and runs a quick RLS check for major deviations or a Shannon entropy check for that restlessness.
Low power, low cost, running on the edge.
Right. If and only if that low-level guard dog smells something fishy, then it triggers a wake-up. It sends a packet of high-resolution data to the cloud.
And the cloud, with its effectively infinite compute,
Runs the heavy autoencoder to confirm the fault.
That makes perfect sense. It's a tiered defense. You don't call in the SWAT team for a noise complaint, but you have them on speed dial.
Exactly. And that tiered approach is the only way to balance the massive computing needs of AI with the energy constraints of a parked vehicle. You can't drain the 12V battery running a GPU all night long.
Okay, so that's the brain. We have a hybrid AI system, edge and cloud, monitoring for entropy and reconstruction errors. Now let's talk about the body. Pillar 2. Hardware architecture. We are seeing a convergence of two very, very difficult trends. 800-volt architectures and wireless BMS.
And they both present huge challenges. Let's start with the voltage.
800 volts.
Everyone wants 800 volts because everyone wants to charge in 15 minutes. It's the headline feature. It's what sells cars.
Sure.
To do that efficiently, we are switching from IGBT's insulated gate bipolar transistors to SiC, silicon carbide.
SiC is the magic crystal.
Mm-hmm.
Higher efficiency, higher heat tolerance. But I keep hearing from our integration teams that it is an absolute EMI nightmare.
It's a machine gun of noise, a complete nightmare. SiC switch is incredibly fast. We are talking about extremely high DVDT. That's the rate of change of voltage.
How high are we talking?
What?
It can be 50 to 100 volts per nanosecond. When you switch that fast, you create these massive high-frequency harmonics that radiate everywhere.
And the BMS is sitting right next to this thing. It's trying to measure millivolts on a cell, while the inverter next door is screaming at 800 volts, switching at nanosecond speeds.
It's an impossible environment. In the old days, we used optical isolation optocouplers to protect the low voltage logic from the high
It's all
voltage.
practice.
But at 100 volts per nanosecond, optocouplers just fail. The noise couples right across the isolation barrier through parasitic capacitance.
Or they just degrade.
Or worse, the LED inside the optocoupler degrades over time due to the heat in the pack. In an 800V SiC environment, optical isolation is dead technology. You can't use it.
So what replaces it? If I'm an engineer specifying the bill of materials for a 2026 platform, what chip am I buying? What technology am I looking for?
You are buying capacitive or magnetic digital isolation. Full stop. You need components that have a spec called Common Mode Transient Immunity, CMTI.
CMTI.
And that spec needs to be greater than 100 keVzones. That's kilovolts per microsecond.
Mhm.
If your spec sheet says anything less, you are going to have data corruption.
And data corruption in the BMS means what?
It means the BMS thinks the battery is empty when it's full, or full when it's empty, which
It
means
shuts down the car on the freeway.
not an option.
Okay, let's talk about the other trend, the one that frankly scares me the most. Wireless BMS.
Yeah.
We are cutting the communication wires inside the pack.
This is the WBMS, and it's projected to grow at something like a 33% CAGR. The value proposition is just seductive.
I can see why. You remove that heavy copper wiring harness, you save weight, you save cost.
You remove the connectors, which are the #1 failure point in any harness. But the real win, the big one, is automation.
Hell, so...
Robots hate wires. Wires are floppy, they're unpredictable, they don't stay where you put them. It's a nightmare for an assembly robot. If you have wireless modules on the cells, a robot can just pick and place the battery modules into the pack. No more plugging in tiny, fiddly connectors. It could speed up pack assembly by 20%.
I get the manufacturing win. I do. And I get the recycling win, the second life argument, where you can just stack the modules in a warehouse and they can talk to the grid without needing to be rewired.
It's a huge enabler for that.
But you are putting a radio inside a battery pack. A battery pack is a sealed metal box.
It's a Faraday cage.
It's a Faraday cage.
Yeah.
Physics 101 says RF signals do not like metal boxes. They bounce. You get what's called multipath interference.
It's an echo chamber, a hall of mirrors for radio waves. If a reflection of the signal arrives 180 degrees out of phase with the direct signal, they cancel each other out.
You get a null, a dead
A
zone.
dead zone.
Okay.
And you lose communication with the cell. If you lose comms with even one cell, you have to shut down the car because you don't know the voltage of that cell anymore. It's a safety requirement.
So how are the chip makers, the analog devices and the TIs of the world, how are they solving this? What's the strategy?
They're abandoning the 2.4 gigahertz proprietary protocols, which were basically, beefed up Bluetooth. They are moving to UWB ultra-wideband.
UWB. Why is ultra-wideband better for the echo chamber?
Because it works differently. Instead of a continuous wave, it uses very short, sharp pulses. We're talking nanoseconds wide across a huge frequency spectrum.
And why does that help?
Because the pulses are so short, the echo arrives at the receiver distinctly after the main signal. They don't overlap and cancel out. The receiver's digital signal processor can actually distinguish the direct path from the reflection and lock onto the first one it hears.
So UWB is like a hearing aid that's smart enough to filter out the echo.
That's a great way to put it. Effectively, yes. Plus, it has lower latency. But of course, it adds costs.
Always a trade-off.
Always. The strategic takeaway here. If you're building a budget city car, maybe stick to wires for now. But if you are building a premium 800V platform that's designed for automated assembly and secondary grid storage, you have to master UWB. You just can't use Bluetooth in a Faraday cage and expect 99.999% reliability.
Okay, so we've built the brain, which is the AI, and the body, which is this wireless 800V architecture. Now, pillar 3, the development paradigm. How do we actually build and test this thing without blowing up the lab every week?
This is the shift-left philosophy on steroids. We touched on this already with the autoencoder training. You simply cannot physically test every thermal runaway scenario. It is too dangerous, too expensive, and way too slow.
Right. You need thousands of failure examples to train the AI.
You can't set fire to 5,000 battery packs just to get the training data.
The accountants would definitely have a problem with that. And frankly, the program timeline doesn't allow it.
Not at all. So the solution is EPCM, electrochemical physical models. We aren't just simulating voltage and current anymore. We're simulating the actual ion flow inside the cell.
This is deep physics modeling.
It is. The industry standard is becoming a co-simulation environment. You use a heavy physics tool like COMSOL multiphysics to model the actual chemical ions moving, the heat generation, the dendrite growth, and you connect that model to Simulink via something called FMU, functional mock-up units.
So you have a chemistry lab running inside a computer, talking to the car's control software in real time.
That's exactly what it is. And this allows you to generate synthetic fault data. You can tell the model, simulate a 100-ohm short circuit on cell number 42, and have it start at t equals 3,000 seconds.
And the model just creates it.
The model generates the exact voltage and temperature curves that would happen in the real world. You then feed that synthetic data to your AI, and it learns to spot the fault without ever burning a real cell.
That is the matrix for batteries. It's the only way forward. And this ties directly into the concept of digital twins, right?
The digital twin is the operational side of this same coin. The strategy here is what we call the data loop. You have to connect production data, the end-of-line testing from the gigafactory, with the fleet data coming back from the cars on the road.
Give me a concrete example of why that connection matters so much.
Okay, let's imagine cell A had a slightly higher internal resistance when it left the factory than cell B. It was still within the green spec, but just barely.
So it's a B-grade cell, but it passed the test.
Right. If you don't track that initial state, then 3 years later, when the BMS in the car sees cell A acting a bit sluggish compared to its neighbors, it might flag it as a fault.
Well, false positive.
A false positive. But if the digital twin in the cloud remembers the birth certificate of that cell, it says, oh wait, that's just cell A being cell A. It's always been like that. It's aging predictably. It's fine.
So the context prevents the false alarms.
Exactly. But if cell B, the A grade, perfect cell, suddenly starts acting like cell A, the digital twin says, wait a minute, cell B used to be perfect. Something has changed. This is an anomaly. Send an alarm. That context is absolutely critical for reducing false positives in the fleet.
Before we leave this development pillar, we have to touch on the chemistry itself. The report spends a lot of time on LMFP, lithium manganese iron phosphate. It's the new darling chemistry because it's cheap like LFP but has a higher voltage. But the sources all say it's a complete nightmare for the BMS. Why?
It is a nightmare for one specific thing: state of charge estimation.
Range prediction.
Your range prediction. LFP and LMFP have incredibly flat voltage curves. As you discharge them, the voltage barely drops until the very, very end. It just sits at, say, 3.2 volts for hours and hours.
I see the problem.
If you are a BMS trying to guess how much energy is left based purely on voltage, it's like trying to measure the water level in a tank that is infinitely wide and very, very shallow. A tiny voltage measurement error means a huge error in your estimated range.
So you think you have 50% left, but you might only have 20%. That is range anxiety waiting to happen.
That's the definition of range anxiety. The strategy here is to move to DQDV analysis.
DQDV. Explain that.
Instead of looking at the absolute voltage, you look at the derivative, the rate of change of capacity versus voltage. Even on that super flat curve, there are tiny characteristic bumps or peaks in the derivative that correspond to specific chemical phase changes happening inside the cathode material.
So the BMS is hunting for these almost invisible bumps to figure out where it is on the curve.
That's it. It's hunting for landmarks on a featureless plane. It usually does this during charging pulses when there's more activity. It's a sophisticated game of signal processing to find where you are on the map when the map looks like a blank sheet of paper.
So the key takeaway is, if you're moving to LMFP in 2026, your algorithm team needs to be expert in differential voltage analysis.
Yes, your standard open circuit voltage lookup tables will not work. You will fail.
Incredible. It seems like every single layer of this onion reveals a new, harder math problem. Okay, let's move to pillar 4. Global compliance and market dynamics. This is the world outside the battery pack. This is where the engineering meets the boardroom and the politicians.
And the map of the world is starkly divided. You have 3 major blocks.
Let's start with Asia.
In Asia, specifically China and Korea, they are the scale kings. Vertical integration is the name of the game. You look at a company like BYD and their FinDreams division.
They make everything.
They build the chip, the BMS board, the cell, the pack, and the car. This gives them immense cost advantages and incredible speed. They're absolutely dominating the LFP market.
Okay, so Asia is about scale. What about Europe?
Europe acts as the regulator. The entire focus there is the EU battery passport, which becomes mandatory in 2027, which means we need to be building for it now in 2026.
And what does that passport require?
It requires end-to-end traceability. The BMS is no longer just a state estimator. It has to be a secure black box logger. It has to record the carbon footprint of the cell's manufacturing, the percentage of recycled content, and the entire health history of the pack.
So it's a birth certificate and a complete medical record for the battery.
Enforced by law. If your BMS can't securely store and transmit this data, you cannot sell your car in the European Union. Period.
Okay, that's a huge driver. And then we have North America.
North America is positioning itself as the software innovators. They're influenced heavily by the IRA, the Inflation Reduction Act, to rebuild local supply chains, but technically their focus is on pushing the cloud BMS and AI integration harder than anyone else.
So they're trying to outsmart the Asian scale with better software.
With better software efficiency and more powerful analytics, yes.
And looming over all of this is cybersecurity. The report mentions IS 21434.
This is the scary part for me. As we connect the BMS to the cloud for these digital twins and battery passports, we are opening a door, an attack vector.
And the BMS controls all the energy.
All of it. If a hacker gets in, they don't just steal your navigation data. They could theoretically rewrite the safety limits on the BMS.
So they could tell the BMS, hey, it's okay to charge this cell to 5 volts when the physical limit is 4.2.
Exactly. They could remotely induce a fire. Or, what's probably more likely, a bricking ransomware attack.
What's that?
They hack the fleet, they lock the BMS so the cars won't start, and then they demand a Bitcoin payment to unlock them.
That is a terrifying scenario. Pay up or your entire delivery fleet doesn't move tomorrow morning.
It is. The strategy here has to be secure onboard communication. Every single message on the CAN bus inside the car must be cryptographically signed.
And what about the chip itself?
We need HSMS hardware security modules built right into the BMS microcontroller to store the cryptographic keys securely. Security cannot be an afterthought. It has to be baked into the silicon from day one.
So a key purchasing decision.
A critical one. If your chosen BMS chip doesn't have a dedicated HSM core, you need to change chips, period.
That is a very sobering thought to end the main pillars on. We've covered the AI brain, the 800V body, the virtual testing ground, and this geopolitical battlefield. So let's bring it all together. You're the consultant. I'm the client, the engineering director listening to this. What is my to-do list for Monday morning?
Okay, here is your survival guide, the executive summary of our entire strategy.
Let's have it.
Number 1, abandon the thermistor. Stop relying on temperature for safety. It's too late. You need to build or buy early detection algorithms. You should be looking at autoencoders for the cloud and Shannon entropy for the edge. If you don't have an AI strategy for anomaly detection, you are already behind.
Okay, AI first. What's number 2?
Number 2, embrace the hybrid architecture. Do not try to put all your compute in the car. It's too expensive and power hungry. Use the edge for immediate real-time safety and use the cloud for deep diagnostics and fleet learning. Number 3, harden the hardware. If you're going to 800V, your isolation tech needs to be bulletproof against that high DVDT noise. Look for CMTI ratings greater than 100 kSV, and seriously evaluate wireless BMS, specifically with UWB, if you want to be competitive on pack density and recycling in the long run.
And last one?
Number 4, compliance is a feature. The battery passport isn't a sticker you put on at the end, it's a data architecture requirement. You need to build the secure logging capability into the BMS from the very start of the program.
Excellent summary. Now, we always like to end with a provocative thought, something to keep our listeners awake at night. We've talked a lot about the world of 2026. What happens in 2028 or 2030?
The elephant in the room is, of course, solid-state batteries. Everyone is working on them. But here's the twist that I think people are missing. When we finally move from a liquid electrolyte to a solid electrolyte, the fire risk might go down, but the fundamental physics of the problem changes completely.
How so?
Solid-state batteries breathe heavily, they expand and contract physically and significantly during charging and discharging.
So the whole battery sack physically grows and shrinks.
Yes. There's a significant volume expansion. So the BMS of the future, the solid-state BMS, might not care as much about millivolts or temperature. It might care more about pressure.
Pressure.
We might see the rise of a mechanical BMS systems that are full of strain gauges and pressure sensors to monitor the internal compressive forces of the stack to prevent the solid electrolyte from cracking under stress.
So we go from being electricians and software engineers to being plumbers or structural engineers.
In a way, yes. We become mechanical stress managers.
Yeah.
The job isn't done. The physics just changes.
The job isn't done. The physics just changes. I love that. To our listeners, the lead engineers of the future, you have your roadmap. The BMS is the brain, the body, and now the passport of the next generation of transport. Go build the nervous system of the future.
Good luck.
Thanks for listening to this deep dive. We'll see you next time.